So now that we've had a chance to look at ionic bonding and exactly how cations and anions come together, let's now take a moment to look at the other side of bonding, which is covalent bonds. Now, in a covalent bond, the electrons are quote-unquote shared, and it's not that they're shared, but as we said earlier, we're looking at now atoms that are smaller in size, such as nonmetals, that are actively in a tug of war. They're trying to pull on each other's electrons. Now, the question is, well, why? Why pull on another nonmetal's electrons? And the answer is, as we spoke earlier, electron affinity is what happens when an atom gains an electron. There's a big drop in energy, right? So for a lot of these nonmetals, gaining electrons will actually cause them to become more stable, or another way of saying that, they're going to be lower in energy. Now, what most of these atoms are attempting to do is they're trying to fill up their valence shell, right? Now, when we talk about a valence shell, these are going to be those electrons that were furthest from the nucleus, or the ones that typically occupy the S and P sublevel. Why the S and P sublevel? Because remember, when we do our electron configurations, the highest energy level was always that S or that P. So even if you had something that was like 5s2, 4d10, 5p, right? I keep saying fifth, and I'm referencing the S and the P. When we look at all of those sublevels, the S and the P, what we're going to find is that we're going to see that if you add them all up, the magic number usually is going to be 8, right? So 8 is going to be our magic number. That is typically what we're looking for, and we refer to that as the octet rule. Does that mean that every element will fill up to exactly 8? No, we can have things known as expanded valence shells. Some elements can't fill up the full 8, but typically the magic number, what we're looking to do is we're looking to fill up our valence shell or gain 8 electrons in the valence shell or fill up our octet, right? Any one of those is the same thing. Now, let's take a look and see how all of this occurs. And so what I have here is basically nitrogen and fluorine, right? Now, a single nitrogen is not going to bond with a single fluorine, and that's it. More stuff has to happen. But I want to use these two so we get an idea to see how those electrons start to fill in and work with one another. So what I'm going to do is over here on the left-hand side, we're going to fill in the valence electrons of my nitrogen. So nitrogen is going to have a grand total of 5 valence electrons. It's going to have 2 in the S, so 1, 2. And then he's going to have 3 lone electrons in its P sublevel. Over here on the other side with our fluorine, we're going to find that we have a total of 7 valence electrons. So again, we're going to have 2 in the S, right? And then we're going to have 5 over here in its P sublevel. Now, again, notice, fluorine is so close to being a noble gas. It just needs one more electron, just one more. But it doesn't have it. It has the room for it. Now, when a nitrogen comes into contact with a fluorine, nitrogen is going to pull on fluorine's electrons. And likewise, fluorine is going to pull on nitrogen. Now, without getting into who pulls harder yet, what I can see here is that nitrogen, in essence, is trying to fill up all 3, needs at least 3 more electrons to fill up that P. Fluorine is looking for 1 more. So what we're going to see happen is that one of these electrons, I'm just going to pick, sake of argument, let's say this one way out here, whoops. So this electron out here is now going to come under attack from the fluorine. And this electron here is going to come under attack from the nitrogen. And what we're going to see is that for the nitrogen, this electron is now going to go into flux, meaning sometimes it's going to be over here, so I'm going to kind of draw them in dash. But other times that same electron is going to be over here. Well, what happened to fluorine's electrons? Well, fluorine's electron, in a similar fashion, is going to go into flux as well. Sometimes he's going to be over here, so I'm drawing him with that little dashed line. But other times, he's going to get pulled in by the nitrogen over here. Now, in this case, what has happened? Because this electron pair is moving back and forth rather quickly, the fluorine looks, again, looks like it now has a full valence shell. Because at any moment in time, it's possible to find 8 electrons in its s and p sublevels, or all of the outermost sublevels, its valence shell is totally filled. Now, is nitrogen happy yet, quote unquote? And the answer is no. It has 2 unpaired electrons. So maybe if I put some more fluorines around it, what we might find is that each of the fluorines is going to interact in a similar fashion. And in doing so, the nitrogen ends up with a full octet, and each of the fluorines is going to end up with a full octet. Now, we're going to talk more about this momentarily because this is a Lewis dot structure that I've drawn over here right below me, right? But this is just so that you see how a covalent bond actually gets formed. It is this tug of war back and forth. Now, as I said earlier, does that mean that everything is going to be a perfectly even pull? And the answer is no. Now, in this case, what you see down here is I formed the 1 electron pair. Now, what I've drawn this circle around, we refer to this as a bonding site. And when 2 electrons are shared between 2 different atoms, instead of drawing it this way, we're going to say that those electrons have now been paired off, or they've created a bond, and we're going to designate that bond with a single dash. So when you see a dash, this represents 2 electrons that are being shared, right? So if I were to count the number of electrons in total, valence electrons in total, around the fluorine right now, I would go 1, 2, 3, 4, 5, 6, and then 7, 8. Cool. If I looked at nitrogen and did the same trick, I would go 1, 2, 3, 4, 5, 6. Ruh-roh! It does not have yet that full octet. That's why it would probably require more fluorines to come in and interact with it. So now let's ask the question, does that mean that if nitrogen and fluorine were to get into a tug of war, they're both going to evenly pull on each other's electrons? And the answer is no. We refer to this as bond polarities, and they come from electronegativity differences, right? So what do we mean by this? Let's take a look. So let's say that I had 2 perfectly sized elements. In this case, let's say that I literally had a fluorine here next to another fluorine here. As we said in a previous episode, if I put a valence electron right there, right at the threshold between atom 1 and atom 2, because it is almost equidistant between the nucleus of the first fluorine and the nucleus of the second fluorine, no one side outpulls it, and as a result, it's going to be a nice evenly distributed electron cloud. We would refer to this as a non-polar covalent bond. Okay, non-polar because again, none of the sides wins. There's no tug of war one way or the other. But now let's look at the different scenario. Let's look at something like, let's make this one the nitrogen over here, and let's make this one the fluorine over here. Let's again put the electron right there at the boundary between the nitrogen and the fluorine. Well, now, what do you notice? Well, obviously, it's going to be closer to the nucleus of fluorine than it is to the nucleus of nitrogen. And as a result, because the valence electron is closer to the nucleus of fluorine, let me say it a different way, because fluorine has a greater electronegativity, that means that we're actually going to see the fluorine nucleus tug on this electron. And it's going to tug on that electron enough such that it's actually going to cause the electron cloud to skew. It's going to cause the electron cloud to shift. And what we see is that once the electron cloud shifts, instead of having those 2 perfect concentric circles like I had over here a moment ago, now, again, this is still the fluorine nucleus, this is the nitrogen nucleus. What we notice is that now there are so many more electrons over here on the fluoride side of the bond. And as a result, this has now become a polar covalent bond. And in a polar covalent bond, there is an uneven distribution of the electrons. I use a very fancy word. I call it a shimmy. We've shimmied the electron cloud, right? If you want, you can sit there and just, it dabbed, right? It moved in a direction. And so that's kind of what's occurring. Whenever you see that polar covalent bond, we're either seeing this or we're seeing this, one of the two sides. Right? Now, the technical term for this, of course, this is known as a dipole moment. And the intensity of the electron cloud shimmy, or the intensity of the electron cloud dipole moment, is going to be dependent upon what were the differences in the electronegativities of the two elements.
So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.